Hi. In this video, we are going to continue our discussion of ellipse. We'll do some theory and a few more problems. So we start off with this, the condition that the line Lx plus my plus n equals 0 is a normal to the ellipse x square by a square plus y square by b square equals 1. So how do we find a condition for this? Notice that we have already done a condition for this to be tangent to the ellipse. That condition was a square L square plus b square m square is equal to n square. This was the condition for the line to be tangent. And this comes by solving the line equation with the ellipse and saying discriminant is equal to 0. Right? Now we need a condition for the line to be normal. Right? So if the given ellipse is this, we have seen before that the normal at the parametric point theta, which is a cos theta comma b sin theta, can be given by the equation ax by cos theta minus by sin theta is equal to a square minus b square, right? Now, if this is the equation of the normal and this is the line equation, these two equations must be identical because both are supposed to be normal, right? And if these two things are the same line, then we can write the ratio of their coefficients, right? We can write L by A by cos theta is equal to M by minus B by sin theta is equal to N by minus of a square minus b square. I'm comparing coefficients of these two lines because they are supposed to be identical. They are supposed to be normal, right? So now what we need to do is eliminate theta from these equations. So what I will do is find cos theta and sin theta separately using first and third, you will get cos theta, and using second and third, you will get sin theta. I will do it on the next screen. You will get cos theta is equal to minus an by L into a square minus b square. And you will get sin theta is equal to bn by m into a square minus b square. Once we get this, we can eliminate by saying cos square theta plus sin square theta is equal to 1. That will remove the variable theta. And you get a square n square by L square a square minus b square whole square plus b square n square by m square a square minus b square whole square is equal to 1. And from here, what we can do is a square minus b square by n square can be taken on the other side, and you get a square by L square plus b square by m square is equal to a square minus b square whole square by n square. So this becomes my condition for the line to be normal to the ellipse. Obviously, I don't expect you to remember this condition, but remember the method by which we got it. A similar method can be done for the tangency condition also, right? So you can take the equation of the tangent and compare it with Lx plus my plus n equals 0 and say L and the tangent equation terms are in the same proportion, and therefore get a condition for that as well. Another thing that I wanted to talk about, which is the standard result, which says at most 4 normals can be drawn from a point to the ellipse, and the sum of eccentric angles at of their feet is an odd multiple of pi. So what is the meaning of this statement? This says that in any ellipse from a particular point, you can draw four normals to the ellipse. And what you will get is that the sum of the eccentric angles theta 1, theta 2, theta 3, theta 4, the sum of these angles is an odd multiple of pi. Basically, it is normal here, normal here, normal here, and normal here. And this is a point P. So from any point P, you can draw four normals. That's the theorem, right? So let's think of how we would get this. Equation of normal at theta. We know in the parametric form, it is ax by cos theta minus by by sine theta is equal to a square minus b square, right? If this normal passes through the point h comma k, passes through p h comma k, then we can put h comma k in this equation and we get ah by cos theta minus bk by sine theta is equal to a square minus b square, right? Okay. So if this is the equation, this is an equation with cos theta and sine theta present. I need to prove that there are four such normals, right? So it should have four different points theta in terms of theta, right? That can only be obtained if you can convert it into a fourth degree equation somehow. So how do I do that? We can take advantage of the trigonometric substitution where cos theta can be written as 1 minus t square by 1 plus t square, and sine theta can be written as 2t by 1 plus t square, where t is tan theta by 2. These are identities. 1 minus tan square theta by 2 by 1 plus tan square of theta by 2 is equal to cos theta. And similarly, sine theta also can be written as 2 tan theta by 2 by 1 plus tan square theta by 2. What is the advantage of doing that? What that does is you are converting the theta terms to theta by 2 terms, and you would end up getting a fourth degree equation. So if you replace cos theta here with 1 minus t square by 1 plus t square and think of t as tan theta by 2, let's see what comes. You get something like this: ah 1 plus t square by 1 minus t square, and then you get a minus bk 1 plus t square by 2t is equal to a square minus b square, right? Now, if you simplify this, you will have to take a common denominator like this: 1 minus t square times 2t. So you will get basically ah into 2t 1 plus t square minus bk 1 minus t square into 1 plus t square is equal to a square minus b square. After a little bit of simplification, you will get this equation: bk t power 4 plus 2t cube ah plus a square minus b square plus 2t ah minus a square plus b square minus bk is equal to 0. So notice that this is a fourth degree equation in t, right? And t was tan theta by 2. So this will have at most four real roots. And you can say, let's say t1, t2, t3, t4 are the real roots of this equation. If t1, t2, t3, t4 are the real roots of these equations, then obviously there will be angles tan theta 1 by 2, tan theta 2 by 2. These are the real roots basically for the equation. So there are corresponding angles theta 1, theta 2, theta 3, theta 4 corresponding to these four roots, right? So which means that the normals at these 4 points are concurrent at h comma k, right? Also, from these equations, we can see that t square term is missing here. The t square term is missing. So sum of t1, t2, 2 at a time is equal to 0. And you also know the product of the roots t1, t2, t3, t4 is equal to minus plus minus plus. So it is equal to minus 1. So product of the roots is equal to minus 1, right? So let's think about what is the implication of this. So what we know is T is tan theta by 2. So that means T1 is tan theta 1 by 2, T2 is tan theta 2 by 2, and so on, right? And we know sum of T1, T2 terms is 0 and T1, T2, T3, T4 is equal to minus 1. Now, if you have to do the expansion of tan of T1 plus T2 plus T3 plus T4 by 4, in trigonometry, you will learn that whenever you have tan A plus B plus C plus D, more than 3 terms, usually it is done like this. It is S1 minus S3 by 1 minus S2 plus S4 and so on. This is the sequence. You can read this theory in SL Loney. Go through SL Loney. There is an expansion for tan A plus B plus C plus D and all. Here S1 and S2 and S3 represent sums of the terms taken one at a time, two at a time, three at a time, and so on. So here S1 stands for sum of all the T1s. S2 stands for sum of T1, T2. S3 stands for sum of all terms like this. S4 is sum of all the terms like this, 4 at a time, but there is only one term like that, T1, T2, T3, T4, and that is equal to minus 1. And S2 is also 0 for us, right? So this value is becoming sum of all the T1s minus S3. We don't know what that is. So, but we know that it is going to be written as minus sum of T1, T2, T3. But look at the denominator. It is 1 minus 0 plus S4 is minus 1. And there is no other higher term because there are only 4 terms here. So you'll not get an S6. So this becomes 0 because the denominator becomes 0. The numerator is not 0. Denominator is 0, which means your tan term is tending to infinity, which means T1 plus T2 plus T3 plus T4 by, it is not a by 4, it is by 2, should be equal to n pi plus pi by 2, right? That is the solution for tan. And that means if you multiply by 2 on both sides, you get T1 plus T2 plus T3 plus T4 should be equal to, okay, I am making a mistake here. When I did tan, I was not intending to do T1, T2. It was tan of theta 1 plus theta 2 plus theta 3 plus theta 4 by 2, obviously. T1 was itself tan theta by 2. I'm taking tan of all the angles, right? So here I'm getting theta 1 plus theta 2 plus theta 3 plus theta 4 by 2. And therefore, that should be equal to n pi plus pi by 2. And from there, we can conclude that theta 1 plus theta 2 plus theta 3 plus theta 4, I multiply by 2 on both sides, is 2n pi plus pi, which is 2n plus 1 pi, which is an odd multiple of pi. So what this tells us is that it is possible for 4 normals to be concurrent at a point. And if that happens, the foot of these points from where the normals were drawn have parametric angles theta 1, theta 2, theta 3, theta 4. Those angles are such that they will add up to an odd multiple of pi. So that is the conclusion. And it comes by getting the 4th degree equation in theta by 2, right? Using the tan substitution. Now we'll do some solved problems. Let's look at question 1, which is if point P theta and D pi by 2 plus theta are 2 points on x square by a square plus y square by b square equals 1, we have to show that the locus of the point of intersection, locus of the point of intersection of tangents at P and D to the ellipse is x squared by a squared plus y squared by b squared equals 2. So the question is asking us to find the locus of the point of intersection to the tangents of the ellipse at these two given points. Okay. So at p theta, equation of the tangent would be x by a cos theta plus y by b sine theta equals 1. And at d, which is pi by 2 plus theta, the equation would be x by a cos of pi by 2 plus theta plus y by b sine of pi by 2 plus theta equals 1. And this equation can be simplified using basic trigonometry. This is minus x by a sine theta plus y by b cos theta equals 1. We have to find the locus of point of intersection of these two tangents, right? So the way to get that locus is to eliminate the variable theta from these two equations. So the idea is here, if you square and add, think about it, if you square this term and square this term and add it, what will come? X by a cos theta plus y by b sine theta whole square plus minus x by a sine theta plus y by b cos theta whole square will be equal to 1 plus 1, 1 square plus 1 square. And this will immediately cancel the 2xy by ab cos theta sine theta term. And the other terms will add up nicely. X square by a square cos square plus x square by a square sine square will become simply x square by a square. And here y square by b square sine square plus y square by b square cos square will become y square by b square. And that becomes 2. How are we able to eliminate theta and get the locus? Technically, what we are doing is we are saying the point h comma k lies on both tangents. And if h comma k lies on both tangents, we can put this h comma k in this equation and put h comma k in this equation also. And ultimately, then your job is still the same, right? After putting h comma k, you still have to eliminate the theta variable, right? And for eliminating theta, you would do this only, square and add. And after that, you would replace h and k with x and y. So I'm directly doing it. I'm just skipping this step where you have to put h comma k in, right? So that is the first problem. Second problem is prove that the chord joining points P alpha and Q beta on x square by a square plus y square by b square equals 1 subtends a right angle at the vertex A. The vertex A is a comma 0. Then tan alpha by 2 times tan beta by 2 is equal to minus b square by a square. So if the chord at joining P and Q subtends right angle at the vertex A, then we have to say that tan alpha by 2 tan beta by 2 is minus b square by a square, right? So what we can do is we know that this is the situation. There is a chord like this and the vertex A here. We know that this angle is supposed to be 90 degree, right? So the vertex A is a comma 0. All you need to do is check the slope of this line, and the product of the slope should be minus 1, right? And the point here is a cos alpha b sine alpha, and the point here is a cos beta, b sine beta, and this point is a comma 0. So it's a very simple problem. You write the slopes. Slope of PA is b sine alpha minus 0 by a cos alpha minus a multiplied by slope of AQ is b sine beta minus 0 by a cos beta minus a. This is equal to minus 1. So you can take a common outside from here and you'll get a b square by a square sine alpha sine beta by cos alpha minus 1 multiplied by cos beta minus 1 is equal to minus 1, right? Correct. So what we can do is we can write sine alpha sine beta by cos alpha minus 1 times cos beta minus 1 as equal to minus a square by b square. And now simplify this. Cos alpha minus 1 can be written as minus 2 sine square alpha by 2. And this can be written as minus 2 cos sine square beta by 2. And the top part can be written as 4 sine alpha by 2 cos alpha by 2 sine beta by 2 cos beta by 2. So 4 will get cancelled. 1 sine alpha by 2 and sine beta by 2 will get cancelled here and the powers will go away. And this is basically cot alpha by 2 cot beta by 2 is equal to minus a square by b square. And that implies that tan alpha by 2 tan beta by 2 will be equal to minus b square by a square, the reciprocal. So that finishes off this problem. Let's look at another locus question. This says, question 3, find the locus of the point of intersection of tangents to the ellipse x square by a square plus y square by b square equals 1 at the points the sum of whose ordinates is constant. So, ordinate means the y coordinate. We are given that the points are such that the sum of the y coordinates is constant, right? So let's take the points as P, A cos theta 1, B sine theta 1, and Q, A cos theta 2, and B sine theta 2. We have to find the point of intersections at tangents to P and Q, at P and Q, where we know that B sine theta 1 plus B sine theta 2 is constant. Let's call that constant lambda. That is given in the problem. We have to find locus of tangents at these points, point of intersection of tangents here, right? So let's think about the tangent equation, right? So the parametric form of the tangent equation will be like this: x by a cos theta 1 plus y by b sine theta 1 equals 1. And the other tangent is x by a cos theta 2 plus y by b sine theta 2 equals 1, right? These are the two tangent equations in the parametric form. The point of intersection of tangents, point of intersection h comma k of two tangents at theta 1 and theta 2 are When you solve these equations for x and y, you will end up getting this. H should be a cos theta 1 plus theta 2 by 2 by cos theta 1 minus theta 2 by 2. And k will be b sine theta 1 plus theta 2 by 2 by cos theta 1 minus theta 2 by 2. So technically, you just have to solve the two equations. These two tangent equations, you have to solve for x and y. When you do that solution, you will end up getting this. This is a result that it would be better if you remember point of intersection of tangents at two parametric points. It's a standard enough result that will be useful for you. Just like if you remember in a parabola, when we had 2 points, 80 square, 81 square, comma T1, T2, 81 square comma 281 and 82 square comma 282, the intersection point of the tangents at those 2 points was a t1 t2 a t1 plus t2, right? We have to remember that to solve problems quickly. So similarly here, the two tangent equations at theta 1 and theta 2 intersect at these points. The formulas are not very difficult to remember. You can verify them yourself and check, but this will come out, right? So you need to know this. Now here, I need to find the locus of the point HK, right, where they intersect. So technically, I have to figure out a relation in H and K and try to eliminate the theta 1 and theta 2 somehow, right? So let's see how we will do that. We have this H is equal to this and K is equal to this. So we can say H by A is equal to cos of theta 1 plus theta 2 by 2 by cos of theta 1 minus theta 2 by 2. And we also have k by b is equal to sine of theta 1 plus theta 2 by 2 by cos of theta 1 minus theta 2 by 2, right? Now, we can write h square by a square plus k square by b square as cos square plus sine square by this. So this will be 1 by cos square theta 1 minus theta 2 by 2, right? Okay. Now remember the condition that we had in the problem. We had sine theta 1 plus sine theta 2 b times is equal to lambda, which was a constant. We can write this as 2b using sin c plus sin d formula. This is sine theta 1 plus theta 2 by 2 multiplied by cos theta 1 minus theta 2 by 2 is equal to lambda. This result was available to us earlier, right? So now here we have this condition and we also have k is equal to b sine theta 1 plus theta 2 by 2 by cos theta 1 minus theta 2 by 2, right? So we have this second condition and this is the third condition, right? So we can say that let's right. So what is, we can use this condition and this condition together and say b sine theta 1 plus theta 2 by 2 is equal to k into cos theta 1 minus theta 2 by 2 is the same as lambda by 2 cos theta 1 minus theta 2 by 2, right? So these two things are same. So we get 2k cos square theta 1 minus theta 2 by 2. So now combining this and this, we will get 2k cos square theta 1 minus theta 2 by 2 is equal to lambda, right? So we get 2k by lambda is equal to 1 by cos square theta 1 minus theta 2 by 2. So this is the situation that we have derived. We are using this result and this result to get this equality. When you say b sine theta 1 plus theta 2 by 2 is equal to this and also equal to this. From there we got 2k cos square theta 1 minus theta 2 by 2 is equal to lambda. And from here I get the value of 1 by cos square theta 1 minus theta 2 by 2, which is 2k by lambda. So here we can write it as 2k by lambda here, right? So what we are getting now is h square by a square plus k square by b square is equal to 2k by lambda, right? And if you replace that with x and y, you get x square by a square plus y square by b square is equal to 2y by lambda. This is the equation of the locus of point of intersection of tangents when it was given that the sum of the ordinates b sine theta 1 plus b sine theta 2 was equal to a constant lambda. So notice that it was a slightly clever type of trick to eliminate theta 1 and theta 2, right? So that is something that you should be aware of. Okay, let's move on to the next problem. This is a question from JEE Mains. This says, if a tangent to the ellipse x square by a square plus y square by b square equals 1 meets its major and minor axis at m and n respectively, prove that a square by cm square plus b square by cn square is equal to 1, where c is the center of the ellipse. Okay, so what is the equation of the tangent at point theta? It is x cos theta by a plus y sine theta by b equals 1. Now, this is the tangent equation. So we can write this as x by a by cos theta plus y by b by sine theta. This is the intercept form of the same straight line equation. So it will meet the major axis and minor axis at a cos theta comma 0 and 0 comma b by sine theta, right? So m becomes a by cos theta comma 0 and n becomes 0 comma b by sine theta. And cm and cn are what? A by cos theta and b by sine theta. Cm, because C is the center, which is 0 comma 0. So Cm is A by cos theta and Cn is B by sine theta. And immediately now you will realize that A by Cm is cos theta and B by Cn is sine theta. So it is simply cos square plus sine square theta is equal to 1. So that is the proof, right? Okay, let's look at another problem. Question number 5. The tangent and normal to the ellipse x square plus 4y square equals 4 at point P theta meets the major axis in Q and R respectively. If 0 is less than theta is less than pi by 2 and QR is equal to 2, then show that theta is equal to cos inverse 2 by 3. Okay. So this equation of the ellipse is x squared by 4 plus y squared by 1 is equal to 1. And a random point on it would be 2 cos theta, comma 1 sin theta. This is the point. The equation of tangent would be x cos theta by a. So x cos theta by 2 plus y sin theta is equal to 1. And the tangent will meet the major axis. Major axis is the x-axis, so you'll put y is equal to 0. So it will be meeting it at 2 by cos theta, comma 0. This is the point Q. Similarly, equation of normal would be what? Equation of normal at this point would be ax by cos theta, so 2x by cos theta minus by, so 1 into sine theta, 1 into y by sine theta is equal to a square minus b square, which will be 4 minus 1, 3. And this line will meet the major axis when y is equal to 0. So x will be cos theta by 2. No, not cos theta by 2. Y is equal to 0. If you put, you get 3 cos theta by 2. So it is 3 cos theta by 2, comma 0. Right? This is my r. And they have said that the distance of QR is 2. So we know that you can take the difference between these 2 points. We know that one point was 2 by cos theta, comma 0. That was my point Q. And the R point was 3 by 2 cos theta, comma 0. So the distance between them is 2. So you can say 3 cos theta by 2 minus 2 by cos theta whole square should be 4. And this becomes, after simplifying this equation, will look like this. 9 cos power 4 theta minus 40 cos square theta plus 16 is equal to 0. And this can be factorized. And what you will get is 9 cos square theta minus 4 multiplied by cos square theta minus 4 equal to 0. Now cos square theta can never be equal to 4 because cos theta is less than 1. So from here you get cos square theta is 4 by 9. So cos theta would be plus minus 2 by 3. But the question said that the angle theta was between 0 and pi by 2. So this implies that cos theta cannot be negative 2 by 3. It has to be plus 2 by 3. And that finishes off our proof. Right? Okay, so we have done the theory and we have also discussed some problems. The key things that I wanted to talk to you about in the ellipse chapter are over. The next class onwards, we'll begin the section on hyperbola. So that's it for these 2 chapters. We have finished parabola and ellipse. Once we do all the conic sections, I will do some problems which are slightly more advanced, which will be mixed problems on everything. Okay. So stay tuned for that. Right now, we have finished our ellipse discussion. You should go through the problems yourself, try to solve them by your own methods, and then only look at the solutions. And definitely go through all the videos we have done in this series so far and make your own notes. Whatever I have discussed is sufficient for JEE Advanced. If you understand everything and have taken proper notes and are able to remember what we discussed. So work on that. And that's all for now. I'll see you next time.